Alright guys, welcome back. We're going to be solving another question from the first chapter of Beer and Johnston textbook, Mechanics of Materials. And we have this link AC that has a uniform rectangular cross-section 1/8 inch thick and 1 inch wide, and we need to determine the normal stress in the central portion of the link. So we discussed in the previous videos in the channel that when you're having the link in the compression, the normal average stress would be in the central portion of the link, and when it's in tension, it will be where the pins are located or the holes that pins are located. So let's see if we get the link AC in compression, and if that's the case, that's probably why the question is saying to determine the normal stress in the central portion of the link, but we'll see. So first thing, obviously for finding the normal stress, we need the force in the link AC, let's call it FAC, and we also need the area of the cross section for AC, which is pretty easy to find since we have the dimensions, so that's not a problem at all. But we have to figure out the FAC in the beam, and the way we're gonna do that is we need the free body diagram of this plate that we have. That's what I'm talking about, and let's see what we have in here. So if we draw the free body diagram, so at point P we have a pin, meaning we have both x and y component. Let's call our xy here, so we can call this by, and the other one is bx, and since it's a pin it can rotate freely, so we don't consider any moment in that support. So that's pretty much for B. We also have two tensions from the cable that is attached to two pulleys on the plate, so one of them is this one and the other one is this one. And since it's a single table, obviously we have the same tension in that, which from the question we can see that it's 120 pounds. So this will be 120 pounds force here. And there is also the other one, 120 pounds force on the other side. We have all the information about dimensions, so no worries at all about that. And we have another pin at point A where the link AC is attached to, so we have another pin, meaning we have to consider two forces, X and Y component. But if we look at the link AC, we see that we have a two force member, and if you want to just go over the two force member, when we have a member that there is only two force applying at two ends, that member is called two force member. And the main takeaway from that is that the force will be along the bond that connects these 2 points. So here what we have is the force AC. We have no idea about the direction so far, so let's not assume that it will be in compression for now because we're not sure about that. So just take a random direction. We can go with this direction, which we'll call it FAC. So we can dissolve this into two components because we're going to use later our 2D shortcut in order to find this FAC. So we're going to go with the shortcut that we have for moment. By the way, I have another channel for engineering mechanics question, which is kind of like prerequisite for this course, and I go deep into these moments and the 2D shortcut that I just talked about. So feel free to check that one out if you want to review all these concepts, but I try to cover them very short in these videos for those of you guys that it's the first time that you're visiting this channel. So we're gonna dissolve FAC to X and Y component because later on we're gonna use this for finding the moment. And we know this angle is 30 degrees, so if that's the case, the X component will be FAC times cosine of 30, and the Y component will be FAC times sine of 30 degrees. And that's pretty much everything for the free body diagram. And the easiest way, so obviously we are in equilibrium, which we have two different equations. Sum of all forces equals 0, and sum of all moments about any point that we have has to be 0. So here, since we're interested in FAC, we're not doing the moment about A because that's going to cancel out our FAC, so it doesn't make sense to go with point A. But if we do the moment about point B, it's going to help us to kind of get rid of all the unknowns that we have at point B. So that's great. We'll only end up with the FAC, which is what we're looking for here to find our normal stress. So we're going to go with point B. Again, we are in equilibrium. Sum of all moments has to be 0, and let's see what we have in here. So we're going to call counterclockwise positive as always. And what we have in here is that we have the moment of these 120 pounds force, which as we can see will be a counterclockwise moment. So we have positive 120 times the distance that we have from here to here. And if we get back to the question, we know that that's 2 inches. So basically we have 120 times 2. Again, we are using the 2D shortcut, and as long as we have all the forces in X and Y direction, we only need the vertical distance, which is this distance that I'm talking about. So it's easy enough because we have all the dimensions in this question. So that's that for the 120 pounds on the right side. And if we look at the one on the left side, we can see that the moment is in a clockwise direction about point B. So we have a negative sign, 120, and the distance this time will be what we have from here to here. Getting back to the question, we'll see that that distance is 12. That's about it for the other 120 pound force. And let's go to the FAC. So we have the moment of the Y component of FAC. So as we can see, the moment is counterclockwise. So we have a positive sign FAC times sine of 30 times the distance that we have. So the distance would be the vertical distance. This is the line of action. So it will be this distance. Let's get back to the question. So we're talking about this, which is 10. And I'm going to clean up the directions. And the last one is the FAC cosine of 30, which as we can see is also a clockwise moment. So we have a negative sign FAC cosine of 30 degrees, and the distance would be from B to the line of action. This is the line of action, and that's the distance we are talking about, the vertical distance I mean. So, and let's see what's that. This is pretty much what we have from here to here, which is basically 12 plus this 4, 12 plus 4, or 16 equals 0, and that would be it for this one. So we're going to bring the 120 on the right. So if we look at this, this will be basically minus 120 times 10, and we're going to factor FAC on the left side of the equations, and we're going to bring the 120 on the right side later. So sine of 30 is 0.5 times 10 will be 5. And we have 16 times cosine of 30. That would give us 13.86. And on the right side, we have basically 120 times 10, which will be 1200. So here, if we calculate FAC, so we're going to get a negative sign, as we can see. So 1200 divided by 5 minus 13.86, and that's going to be minus 135.44 pounds, and we got a negative sign, meaning our FAC is in the opposite direction. So what we found in here, so we consider our FAC in this direction, which wasn't correct. So this has to be actually in the other way, but that's the force that is applying to this plate from the link AC. Meaning the link AC in here has the opposite force in this direction. So AC basically is in compression. Now we can confirm that the member is in compression. So this was the case, and that's why the question is asking to find the force in the middle part, and this should be pretty easy. The area is pretty easy to find because from the question, if we do that section, we know it's, let's get back to here. Yeah, so 1/8 thick and 1 inch wide. So that's pretty much the cross section that we have. So the area is basically 1 times 1/8, which will be 1/8 inches squared. So now we have the A and FAC. So FAC over A minus 1. We don't need this negative sign. So basically 135.44 pound over 1/8. And we can see that the normal stress would be 135.44 times 8, which would give us 1083.5 pounds over inches squared, or what we call PSI. So yeah, that would be all for this one. Hope you guys find it helpful. Let me know if you have any question, and don't forget to subscribe to the channel, like and comment, and I'll see you guys in the next video. Have a good one.